Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is power measurement in three-phase AC systems using the 2 Wattmeter method. Our objective is to examine the 2 Wattmeter method employed to measure power in balanced and unbalanced three-phase AC systems. We'll compare and contrast this method with the 3 Wattmeter and the single Wattmeter method and discuss which methods work in which situations and which don't. This lecture operates under the presumption the viewer has more than a passing familiarity with the analysis of balanced and unbalanced 4-wire Y, 3-wire Y, and delta configurations in three-phase AC systems, as illustrated in the three-phase AC examples lecture, available at the Big Bad Tech channel. Additionally, it is presumed the viewer has a nodding acquaintance with both the 3 Wattmeter method and the single Wattmeter method, as illustrated in the single Wattmeter method lecture, also available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. So this lecture doesn't bog down in lengthy calculations, let's just use the results of the aforementioned three-phase AC examples lecture as a jumping off point for our discussion. If you recall, we calculated the electrical properties of a balanced configuration of 3 load elements, where each element is modeled as an impedance of 425 ohms at an angle of 40 degrees, when configured as a balanced 4-wire Y, a balanced 3-wire Y, and a balanced delta configuration in a 60 Hz, 120, 208 volt three-phase AC system. Then we modified one of our impedances to 345 ohms at an angle of 30 degrees and analyzed an unbalanced 4-wire Y, an unbalanced 3-wire Y, and an unbalanced delta configuration in the 60 Hz, 120, 208 volt three-phase AC system. The results for the unbalanced configurations appear before you. You'll note some very predictable outcomes that highlight how different unbalanced load configurations interact with a three-phase AC system. You may want to take a screenshot of this data, particularly the line-to-line voltages, the line current, and the power figures, because we'll be referencing this set for several illustrated examples. During one of the aforementioned lectures, we explored the use of the single Wattmeter method to measure power in balanced three-phase AC systems. The single Wattmeter method is not applicable for unbalanced three-phase AC systems. Today we'll explore power measurement in unbalanced three-phase AC systems using the 2 Wattmeter method. As such, let's zoom in on the data for each of the unbalanced configurations. For the unbalanced 4-wire Y configuration, each load impedance still directly experiences a smaller line-to-neutral voltage. Load current magnitude and relative phase shift for each load is proportional to an Ohm's law manipulation, as is power for each individual load. Given one of the loads is different, current and power for that branch is understandably different. In the unbalanced condition, current travels in the neutral line. Total apparent, total real, and total reactive power is the summation of individual apparent, individual real, and individual reactive power figures. For the unbalanced 3-wire Y configuration, any imbalanced current is left to circulate throughout the system. As such, voltage and current for each branch impedance is different, as is power. Total apparent, total real, and total reactive power is still the summation of individual apparent, real, and reactive power figures. You note for Y configuration analysis, it's a recommended practice to reference everything with respect to one of the line-to-neutral voltages, in this case, L1 at 120 volts at an angle of 0 degrees. If you wanted to be hard-headed about this and reference all your calculations with respect to one of the line-to-line voltages, you have to shift these results by negative 30 degrees or 30 degrees clockwise. As inconvenient as this is, this will become an important consideration for the 2 Wattmeter method. Finally, for the unbalanced delta configuration, each load impedance still directly experiences the larger line-to-line voltage. Load current magnitude and relative phase shift for each load is proportional to an Ohm's law manipulation, as is power for each individual load. In the unbalanced condition, line currents are also different. Total apparent, total real, and total reactive power is the summation of individual apparent, real, and reactive power figures. You'll note for delta configuration calculations, it's a recommended practice to reference everything with respect to one of the line-to-line voltages, in this case L1, L2 at 208 volts at an angle of 0 degrees. If you wanted to be hard-headed about this and reference all your calculations with respect to one of the line-to-neutral voltages, you'd have to shift these results by 30 degrees counterclockwise or positive 30 degrees. The larger point for this particular lecture focusing on three-phase power measurement being this. You already know how to calculate and measure power in three-phase AC systems. AC power consists of real and reactive components, and these different dimensions of power can be calculated for an individual element using any one of the numerous methods at our disposal. Power for an individual load is a complex conjugate of load voltage times load current. Additionally, power for an individual load is a complex conjugate of load voltage squared divided by impedance. And finally, power for an individual load is a complex conjugate of load current squared times impedance. Total apparent, total real, and total reactive power for a three-phase AC system is simply the summation of individual apparent, real, and reactive power figures and will remain so whether the load is balanced or unbalanced, Y or delta, black, brown, red, orange, yellow, green, blue, purple, gray, or white. Again, calculating power for individual elements should be well within your capacity. Total power is simply the summation of individual powers. As we previously discussed in the aforementioned lectures, a brute force 3 wattmeter invasion could directly measure power for a 4-wire Y configured load, a 3-wire Y configured load, or a delta configured load in the balanced or unbalanced condition, where total apparent, total real, and total reactive power is simply the summation of individual apparent, real, and reactive power figures. The 3 wattmeter method is a reliable and robust technique that really lets a user know exactly what's happening to each individual load at any point in time. This being said, implementing the 3 wattmeter method is expensive and time consuming because it necessitates actively digging into the loads to access the test points, the exception being the 4-wire Y configuration, in which all test points are externally accessible. Some loads, like 3-wire Y and delta configurations, don't facilitate invasive inspection. Is there any way to measure power in an unbalanced 3-phase AC system without having to dig into the loads, and perhaps one that uses less equipment and less confusing connections? Indeed there is. This is known as the 2 wattmeter method, and like the previous methods we've discussed, it too has its advantages and associated disadvantages. The 2 wattmeter method makes use of 2 wattmeters, big surprise, configured in the following fashion. Note wattmeter 1 is measuring the line-to-line voltage from L1 with respect to L2, and line current in line 1. Wattmeter 2, however, is doing something interesting. Recall I've encouraged you again and again to simply pick a direction and stick with it when approaching 3-phase AC circuit analysis scenarios. I typically go L1 to L2, L2 to L3, and L3 back to L1. Wattmeter 2, however, is violating this recommendation, as instead measuring voltage from L3 with respect to L2. This is counter to the advice I've been giving you, yet absolutely essential to the 2 wattmeter method. Wattmeter 2 measures current in line L3 in the traditional direction from the source to the load. Given a 120, 208 volt, 60 Hz 3-phase AC system, L1, L2 would be 208 volts at an angle of 0 if we assumed it was the reference. Wattmeter 1 would measure L1, L2 as we've been traditionally presenting it, as 208 volts at an angle of 0 degrees. Wattmeter 2, however, given its flip-flop polarity, would measure L3, L2 as negative 208 volts at an angle of negative 120 degrees, or 208 volts at an angle of negative 120 degrees plus or minus an additional 180 degrees, or alternatively as 208 volts at an angle of 60 degrees. Graphically, L3 with respect to L2 would be the back azimuth or negation of L2 with respect to L3. Note both wattmeters in the 2 wattmeter method are external to the Y or delta configured load and do not necessitate any invasive inspection. If the thought, each wattmeter in the system is reading nonsense, ever crossed your mind, you'd be absolutely correct. In isolation, each wattmeter's reading in the 2 wattmeter method is absolute garbage. If, however, we add the 2 wattmeters readings, we obtain the total apparent, the total real, and the total reactive power. How can this be true? I'd explain, but it'd be a waste of both your time and my time since it's a mathematical goat show of epic proportions and absolutely not essential to the implementation and practical use of the 2 wattmeter method. Long story short, I like to think of the 2 wattmeter method as a means of indirectly monitoring any imbalance in the system by keeping a hand on 2 lines, i.e. the 2 line current ammeters, and a foot on the other, i.e. making use of the other line as our reference. With 3 points of contact, the truth can be squeezed from this system. Note the 2 wattmeter method is entirely external to this system. It works for either Y or delta configurations, and for damn sure it's a lot easier to implement than the 3 wattmeter method. The principal distinguishing characteristic of the 2 wattmeter method, in contrast to the single wattmeter method we discussed in a previous lecture, is that it is suitable for both balanced and unbalanced loads. Allow me to demonstrate. Let's take a look at the 2 wattmeter method employed in our example unbalanced delta configuration. If you recall, we obtained the following data during the 3-phase AC examples lecture for an unbalanced delta, where one impedance, ZAB, was modified to 345 ohms at an angle of 30 degrees, and impedances ZBC and ZCA remained 425 ohms at an angle of 40 degrees. Load current and power experienced by unmodified impedances ZBC and ZCA remained unaffected, whereas load current and power experienced by the modified impedance ZAB changed in comparison to our balanced delta. Given these modified conditions internal to the delta, line currents I1 and I2 external to the delta also changed. Total apparent, total real, and total reactive power was the summation of individual apparent, real, and reactive power figures. Ideally, the 2 wattmeter method should yield these same results. However, it will be easier and cheaper to implement and necessitate no invasive inspection as would a 3 wattmeter method. Recall the calculations we made for the unbalanced delta configuration made use of L1, L2 as our reference. As such, we don't really need to compensate for any phase-shifted offset between a line-to-line and a line-to-neutral voltage, since the 2 wattmeters central to the 2 wattmeter method are reading the line-to-line voltages. This will not be true for the unbalanced Y configuration, a follow-up illustrated example. Note wattmeter 1 measures line 1 with respect to line 2 and line current in line 1. Wattmeter 2, however, is flip-flopped and measures line 3 with respect to line 2 and line current in line 3. Wattmeter 1's line 1 to line 2 voltage reading would be 208 volts at an angle of 0 degrees, and its line L1 current reading would be 897.1 milliamperes at an angle of negative 60.8 degrees. Current lags voltage by a relative 60.8 degrees. Application of the AC power formula demonstrates wattmeter 1 would display 186.6 volt amperes, of which 91 watts is directed towards real power and 162.9 VARs is directed towards reactive interchange. Taken in isolation, this wattmeter's reading is garbage because it's not the whole picture. Wattmeter 2's voltmeter is flip-flopped. Wattmeter 2's line 3 to line 2 voltage reading would be 208 volts at an angle of 60 degrees, and its line L3 current reading would be 147.7 milliamperes at an angle of 50 degrees. Current would lag voltage by a relative 10 degrees. Application of the AC power formula demonstrates wattmeter 2 would display 176.3 volt amperes of apparent power, of which 173.6 watts is directed towards real power and 30.6 VARs is directed towards reactive interchange. Again, taken in isolation, this wattmeter's reading is also garbage because it's not the whole picture. If, however, we add wattmeter 1's reading with wattmeter 2's reading, we obtain a total real power figure of approximately 264.7 watts and a total reactive power figure of 193.5 VARs. Packaging these as the real and imaginary components of a complex number in rectangular format, we can convert it to polar format as 327.8 volt amperes, which yields our total apparent power figure. These figures closely match those we obtained in our previous analysis. The advantage being that the 2 wattmeter method is external to the delta configured load and we're using less equipment. Let's now take a look at the 2 wattmeter method employed in our example unbalanced 3-wire Y configuration. If you recall, we obtained the following data during the 3-phase AC examples lecture for an unbalanced 3-wire Y configuration, where one impedance Z1 was modified to 345 ohms at an angle of 30 degrees, and impedances Z2 and Z3 remained 425 ohms at an angle of 40 degrees. Given imbalanced current is left to circulate throughout the system, almost every aspect of the unbalanced 3-wire Y configuration changed compared to our previous balanced 3-wire Y configuration. Not only is current different for every branch impedance, so is voltage. Understandably, power figures for each branch impedance differ. Total apparent, total real, and total reactive power is the summation of individual apparent, real, and reactive power figures. Ideally, the 2 wattmeter method should yield these same results, however, be easier and cheaper to implement and necessitate no invasive inspection. Recall the calculations we made for the unbalanced 3-wire Y configuration made use of L1 with reference to neutral as our reference. Given the 2 wattmeters central to the 2 wattmeter method are not reading line-to-neutral voltages, but rather the line-to-line voltages, we do need to compensate for the phase-shifted offset between line-to-line and line-to-neutral voltage. As such, each voltage and current figure would experience a 30-degree clockwise or negative 30-degree offset when L1, L2 is employed as a reference. I will readily admit this is a real pain, but it's essential if our analysis is to yield correct results. Again, this is for demonstration purposes only, and actual implementation of the 2 wattmeter method is a lot easier than I'm making this out to be. Again, in practice, one would simply add up the readings for the 2 wattmeters to obtain total power. Really, we only need to compensate for L1 and L3 current values. Line L1 current reading would be 324 milliamperes at an angle of negative 33.8 minus an additional 30 degrees, or negative 63.8 degrees if we employed L1, L2 as our reference. Similarly, line L3 current reading would be 278.4 milliamperes at an angle of 85.4 degrees minus an additional 30 degrees, or 55.4 degrees using our new reference. Power figures remain unaffected. Note Wattmeter 1 measures line 1 with respect to line 2 and line current in line 1. Wattmeter 2, however, is flip-flopped and measures line 3 with reference to line 2 and line current in line 3. Wattmeter 1's line 1 to line 2 voltage reading would be 208 volts at an angle of 0 degrees. Again, we're assuming L1, L2 to be our reference, and this wattmeter's line L1 current reading will be 324 milliamperes at an angle of negative 63.8 degrees. Current would lag voltage by a relative 63.8 degrees. Application of the AC power formula demonstrates wattmeter 1 would display 67.4 volt amperes of apparent power, of which 29.8 watts is directed towards real power, and 60.5 VARs is directed towards the reactive interchange. Taken in isolation, this wattmeter's reading is garbage because it's not the whole picture. Wattmeter 2's voltmeter portion is flip-flopped. Wattmeter 2's line 3 to line 2 voltage reading would be 208 volts at an angle of 60 degrees, and its line L3 current reading would be 278.4 milliamperes at an angle of 55.4 degrees. Current lags voltage by a relative 4.6 degrees. Application of the AC power formula demonstrates wattmeter 2 would display 57.9 volt amperes of apparent power, of which 57.7 watts is directed towards real power and 4.6 VARs is directed towards the reactive interchange. Again, taken in isolation, this wattmeter's reading is also garbage because it's not the whole picture. If, however, we add these two wattmeter readings, we obtain a total real power figure of approximately 87.4 watts and a total reactive power figure of approximately 65.1 VARs. Packaging these figures as the real and imaginary components of a complex number of rectangular format, we can convert it to polar format as 109 volt amperes, which yields our total apparent power figure. These figures closely match those we obtained in our previous analysis, the advantage being that our 2 wattmeter method is external to the Y-configured load, and it uses less equipment than the 3 wattmeter method. Again, don't necessarily concern yourself too much with referencing and re-referencing for actual implementation of the 2 wattmeter method. The only reason we had to do this for this particular illustrated example is because we initially chose L1 as our previous reference. Lacking access to the neutral node, this wouldn't be an option. We'd have to choose something accessible as our reference, in this case, line 1 with respect to line 2.